like to welcome Philip Brown. So, Philip, joined remotely. Okay.
All right.
So,
Hello, my name is Philip Brown, and thank you very much to the organizers for allowing this remote presentation to happen. So what you see in the picture there is about what my hometown looks like right now. There's snow all over the ground. It's very cold, and the roads were too icy for me to make my flight a few days ago. So thanks very much to the organizers. So I run a multidisciplinary research lab at the University of Colorado, and we study a type of system I call a sociotechnical system. So I'm interested in systems where there is an engineered piece coupled with a social piece, and it's the interactions between the two and the decisions of the various people in the two pieces that yield the performance of the overall system. So for example, the early examples of these are things like eBay, the e-commerce platforms that we grew to know and love 20 years ago. And then now we're seeing this proliferation of smart X, so smart grids, smart devices, smart homes, and those all share aspects of this system. And then of course, the cryptocurrency blockchain space is right at the core of these kinds of things, right? We have to understand the interactions between the users of systems and the design of the system. So these kinds of systems present a huge variety of challenges to engineers. They tend to be large and complex. They tend to have lots and lots of uncertainty. And then my favorite point is that the optimizees in our systems tend to be optimizers themselves. Right? So if I want to incentivize my users or my customers to behave in a particular way, I can't just tell them what to do. I can't just directly optimize their behavior. I have to give them incentives so that they optimize their own behavior. So the case study I'm looking at in this paper is a decentralized stablecoin problem. So the core problem is this, and I'm assuming that most of you are familiar with the kind of the core of the problem, but here's my simple description of it. We want a cryptocurrency that has some kind of mechanism that ensures it has a stable price and some kind of decentralized governance system. So Bitcoin doesn't fit the bill because even though it is a cryptocurrency and it has some kind of ad hoc decentralized governance, it does not have mechanisms that regulate its price. I'm also not talking about stablecoins like Tether. Right? Tether is a cryptocurrency. It has mechanisms to maintain a stable price, but it doesn't really have a plausible claim to decentralized control. So I'm talking about systems like DAI and BitUSD, BitCNY, right? So these are stablecoin systems they're digital currencies operating on blockchains, so they're cryptocurrencies, and they have some kind of inbuilt mechanism for decentralized governance. And the question is, how can we design incentive mechanisms so that the price is stabilized via their decentralized governance? And so now is a good time to acknowledge my funding source. So this work is funded by the BitShares blockchain through their decentralized funding mechanism. So I thank my sponsors for this. So today I'll be focusing on the stable coins that are native to the BitShares blockchain. Okay, so the stablecoin problem, whether it's centralized or decentralized, is essentially a supply regulation problem. If the price of your stablecoin goes up, you need a way to increase the supply of the coin to sell into the market to bring the price back down. And likewise, if the price drops, you need a way to purchase tokens on the market, remove them from supply, and bring the price back up that way. So if you can control the supply of your stablecoin in a centralized way, this is a relatively straightforward problem. When the supply goes up, you just print new stablecoins and sell them. Right? If you have control over supply, you can just do that. And then if the price goes down, you purchase outstanding tokens and destroy them, removing them from the supply. And the real challenge here is just that you don't run out of cash to purchase the outstanding tokens. And it's not a trivial challenge, but at least we can specify it and say exactly what it is. So if we transition to the decentralized paradigm, now instead of being able to say we issue new tokens, now we need to design an incentive mechanism so that the participants in our system themselves print new tokens whenever they're needed, right? When the price rises too high, participants create new tokens and sell them into the market. And then possibly even more difficult, we need an incentive so that the participants in our system purchase stable coins, and destroy them when the price drops too low. right? So today we're going to talk a little bit about how BitShares does this, and then I'll present some analysis that we've done, kind of assessing the systemic risks associated with these kinds of systems. And we'll talk about some general takeaways that hopefully can apply to other platforms as well. Okay, so let me introduce you to our trader, Alice. So Alice starts life with a pot of BTS core tokens. So that's the core token of the BitShares blockchain. And she has a queue of them to begin with. And she wants to create a stablecoin, BitCNY. So she wants to print new stablecoins that are pegged to the value of the Chinese national currency. So what she does is she takes her core tokens, she commits them to the blockchain, so she locks them away on the blockchain and receives a loan of BitCNY, of this stablecoin. So she chooses how much of these stablecoins to get by choosing her collateral ratio. So she chooses how many stablecoins to get, or the value of the stablecoins she gets, as a function of how much collateral she committed. And essentially here, what you need to see is that if she chooses a large collateral ratio, this means she has a small debt, right? This means the value of her stablecoins that she just borrowed is small in comparison to the total value of the collateral she committed. So why would she do this? Well, Alice is a BitShares bull. So Alice believes that the price of BitShares is going to go up in the future, and she wants leverage. So what she'll do is she'll take her new loan of stablecoins, she'll sell it into the open market for BitShares tokens, and then she'll sit on those BitShares tokens waiting for the value of BitShares to go up. Okay, so here's the basic picture. At some initial time, she opens her collateral position, then time passes. Then she closes her collateral position and realizes whatever profit or loss is intrinsic there. So when she closes her collateral position, she has to purchase back BitCNY, give it to the blockchain, and then she receives her collateral back because she's paid off her debt. So in the intervening time, the value of her collateral and the value of the proceeds of her initial sale has changed by a factor of D. Right? So if D is greater than 1, this means the price of BitShares went up. If it's less than 1, the price of BitShares went down. Okay, so at the beginning, she has Q over R BitShares tokens in her account, plus the Q in collateral. She has a debt, she owes a debt of Q over R BitCNY. And then at the end, when she wants to close her position, she still has that many BitShares tokens. But now the value of her debt has changed relative to the value of her BitShares tokens, right? So we're imagining she's a BitShares bull, so she's doing her accounting in BitShares, so all she cares about is how many BitShares she has at the end. So notice here that if the value of BTS went up, so the market price of BTS went up, then the value of her debt relative to the value of her collateral went down. And vice versa, if the price of BitShares goes down, then the value of her debt goes up, and she's going to have to pay back more than she borrowed. So when she closes her position, if she has plenty of collateral left, then this expression gives us a measure of her profit. So she still has the Q over R from the proceeds of her sale, minus the debt, which is now changed value from when she borrowed it. Right? And her hope is that her debt is now worth less than it was when she borrowed it, so she'll be able to pay it back more easily and realize a leveraged profit. So on the other hand, if this value of D drops too low, so if BitShares is in some kind of a bear market, and she doesn't have very much collateral left, but she still has enough to cover the debt, then the blockchain assesses her a margin call penalty. So we capture that penalty with this parameter S, and S says, here's how much more you have to pay back on top of your original debt because we're penalizing you for not maintaining your collateral high enough. And then if she doesn't have enough collateral, if she's insolvent, then the blockchain just takes all of her collateral and all she's left with is this Q over R. Okay, so her decision problem ends up not being trivial. So this is a set of traces of her profit and loss function as a function of the change in BitShares price. Okay, so if you look at the blue curve, for example, the top curve on the right, if the price of BitShares went high and she didn't put much collateral up, that means she took out a large loan relative to the value of her collateral, then she realizes a large profit. If the BitShares price goes very low, then in all cases she realizes some kind of a loss. And so I'd love to speak with people offline about why these particular sets of curves are challenging. But these curves, it turns out, don't do exactly what we would hope. But nevertheless, they're curves, she can compute them, and so if she's trying to make a decision about how much collateral to put down, let's assume that she's going to do so rationally. So her beliefs will be consistent with her actions, and so she'll assume some distribution from which this price disturbance is drawn, and then try to maximize her expected profit given that distribution. And so in the paper, we study a log normal distribution, but of course we could replace this with some kind of heavy tail distribution, which could also be reasonable. Okay, so Alice wants to select her collateral ratio R to maximize her expected profit, given her belief of the future. But what does BitShares want here? So BitShares has two nominally competing goals. So one, they want Alice to choose a low collateral ratio so that there are lots of stablecoins in the market, so we have liquidity. At the same time, they want her to choose a large collateral ratio so that the stablecoins she does create are well collateralized. And so BitShares can control this through a decentralized mechanism with two different parameters. So one, they can define a parameter M, which is a threshold that says this is what we mean when we say enough collateral. And if your collateral drops below this threshold M, then we charge you a margin call penalty. And then they can also choose the value of the margin call penalty. And that's the penalty that she pays on top of her debt for not having enough collateral at the end. All right, so BitShares is going to, in some decentralized way, they're going to select M and S, knowing that Alice will optimize accordingly. Then Alice will select her collateral ratio to maximize her profit, given M and S and her beliefs. And the overarching question that we ask is, what is the probability that results from this decision-making process that Alice will default? That at the end, she won't have enough collateral left to cover her debt. So first, what we're going to do is analyze her decision problem. And so these are curves where we plot the limit on collateral ratio that we've put on the bottom. So M is on the horizontal, or sorry, her collateral ratio that she could choose is on the horizontal axis. And then her expected profit given some distribution is on the vertical axis. And then the different traces correspond to different collateral requirements that we place on her. So if we have a low collateral requirement, like the blue curve, her optimal profit is to minimize her collateral ratio, right? To borrow as much as she can. On the other hand, if you look at the brown trace on the bottom, if she has a high collateral requirement, her optimal choice is not to maximize her leverage. Instead, it's to act in a slightly more moderate, slightly less risky way. So instead of choosing the 1.7 that she's allowed to, she chooses a 2.1. So what does this mean? So this means that if we allow her to be risky, to be very risky, she will be very risky. If we force her to be slightly less risky, then she'll be even less risky than we're asking her to be, right? And this is just an emergent property of the particular incentive system that we have set up right here. And it turns out her decision is highly dependent on the margin call penalty as well. So this is a plot where we plot that M parameter on the horizontal, so the collateral we're requiring her to put down on the horizontal. Then we're plotting her optimal decision on the vertical. And notice in particular that orange line has a discontinuity in it, right? So this is worrisome. So what this means is that if our collateral requirement is about 1.53, we have no idea what Alice is going to do. Alice might choose about 1.53, or she might choose something much, much less aggressive, something like 1.9. And there's this discontinuity in here where her decision is highly sensitive to our incentive choice. So even more worrisome is this plot. So this plot captures a measure of systemic risk in the system. So the vertical axis here, it represents the probability that she will default on her loan, so she will not have enough collateral at the end. And the horizontal axis represents our constraint on her collateral that she puts down in the first place. And notice here that there is an order of magnitude discontinuity in the probability that she will default. Right? So this means that it's very difficult to control exactly what her behavior is going to be. And it can be very difficult to predict what the outcomes will be. Okay, so just to wrap up, what we've shown is that the systemic risk in the system is extremely sensitive to incentives. But what this actually also means is that the stablecoin supply and the liquidity thereof is extremely sensitive to our incentive parameters. So this suggests that there may be an inherent tension between risk and liquidity in these stablecoin systems. And this is something that I suspect is true overall. I suspect it's true broadly in many different decentralized stablecoin systems. So moving forward, we need to look at this in a dynamic context instead of just in the one shot that I looked at it in this thing here. So there's lots of questions related to dynamics. There's also lots of questions related to game theory, right? In the real world, Alice isn't a single person, right? Alice is this model of many, many different people who are all trading on the market all at once. So I'm seeking collaborators, and if you're interested in looking at this kind of problem with me, please contact me, because there's a lot of questions that we have left to answer. So with that, I'll open it for questions if there's any time. Otherwise, thank you very much.
Thank you very much, Philip.